right, so section 9.2 is on infinite series. And we started talking a little bit about series last time when we started talking about sequences, a portion of what's going on today. So to start with, we're going to talk about convergence. So if we have a sequence of partial sums, this is the summation from k equal 1 to n of a sub k, so only a portion, we're not going all the way to infinity. But if this sequence of these sums converges to some value s, then if we were to write this same summation and it goes to infinity, it is the limit of this sequence of partial sums. We call S the sum of the series, and alternately, if we have a series that doesn't converge, then it diverges. And we're going to talk about some different kinds of series that do these things. And the first one we're going to talk about, we encountered last time as a sequence. We actually encountered it 2 class periods ago as a sequence. And now we're going to talk about it as a series. Go ahead and jot those down. Aren't you glad you're not writing all of that down? Yeah. So the idea behind this is that if we took the summation of the first 3 terms, and the summation of the first 4 terms, and the summation of the first 5 terms, and 6 terms, then we could take each of those summations and call them S1, S2 for the first 2 terms, S3 for the first 3 terms. And we could make a series out of that, or a sequence, out of that. And we could look at what happens as that sequence gets infinitely large. And if that sequence converges, then the original summation that actually went to infinity would also converge. And if that original that sequence of s sub n's diverges, then the series as it went to infinity would diverge. So the first sequence or series that we're going to talk about is a sequence we talked about before. It's a geometric sequence. So a geometric sequence can be written in the form where we have a summation from k equals 0 to infinity of a times r to the k. It looks like arc. We created these last time. You created them on your homework, or at least you could have created on your homework had you encountered a geometric sequence. You actually didn't. You actually only encountered some arithmetic ones. But we did a geometric one in class. And so these always have the pattern that you multiply by a value to get to the next value. Do you remember that from last Friday? So the a value at the beginning is actually the first term in the sequence. And then the r to the k, the r value is called the ratio or the common ratio. And then the k value is the exponent that keeps that repeated multiplication going on. All right, so our theorem that talks about this geometric series says that if we have this geometric series, that it will converge to a over 1 minus r when the absolute value of r is less than 1. And it will diverge if it's greater than or equal to 1. And I've mentioned it before, and it's actually written here now that r is referred to as the ratio, or you may hear me say common ratio. Some books will use that terminology. So the convergence is all based on the value of r, which is the value that's raised to the exponent. And the sign doesn't matter, right? It doesn't matter if r is positive or negative. All we're concerned with is if the numerical value aside from its sign is either greater than, equal to, or less than the number 1. Everybody good so far? So identifying whether a series converges when it's a geometric series is relatively easy. The first thing you have to verify to yourself is that you really have a geometric series. Because we're very quickly going to get into section 9.3 where we're not going to be told, hey, this is a whatever kind of series. You're going to have to be able to look at it and say, this is this kind of series. It's kind of like when you did integration. At some point, nobody told you, hey, you have to use integration by parts on this problem, right? This is the same thing. So looking at this one, do you see that it's a geometric series? Can you see the pattern? It's got something raised to a power of k, and it's got a coefficient in front of it. If it didn't have that 1/2 in front of it, it would have a 1. It understood 1 in front of it. That'd be okay as well. But the crucial part is that it has some value that's raised to the power of k. Okay, everybody good so far with that one? Okay, so it is a geometric series, yes? So the question is whether or not it converges. And if it converges, we're going to find the value it converges to. Does this series converge? Yes. Why? Right. What is r on this one? It is. It's actually -1/3, right? So my r value here is -1/3. And the absolute value of -1/3 is, in fact, less than the number 1. Right? This is what we're doing. And so because of that, this converges. Now, I mentioned in class last time, you don't have to write sentences for me, per se, but you can write a little bit of a justification down. So if you just say converges, that's probably not going to be okay, because I don't know if you even identified the r value right. Were you looking at the 1/2 or the 1/3? I mean, I don't know, because either of those, if you interpreted that to be r, would look like the thing converged. So I want to make sure that you know which pieces you're looking at. This does, in fact, converge, which means we can actually find the value it converges to. We're very quickly going to not be able to do that anymore. But if it's geometric, we can. So this is a unique problem. Geometric series, we can find the convergence value. All right, so we do that with this formula, a over 1 minus r, right, that we saw on the previous slide. So we're going to use that. My a value is what? 1/2. And we're doing that over 1 minus, and my r value was that -1/3. And you do need to have the negative. It's part of the r value. It's ignored in the sense of whether it determines whether it doesn't determine whether it converges or not. But it does change the value of the convergence of the series, okay? So we do need that in there. So I've actually got 1/2 over what here? 4/3, which is 1/2 times 3/4, yeah? Which gives me a total of what at the end? 3/8. So if we added all of the terms, as if that were possible because this is an infinite series, but if we added all of the terms, or infinitely many of the terms till it gets to infinity, it would get very close to the value 3/8, right? That's what this is saying. Okay. What would we need to change in this particular series in order to make it divergent? What would have to change to make this diverge? Yeah, exactly. So we would have to have an r value where the absolute value of r is greater than or equal to 1. Actually, equal to 1 would cause just as much problem. It would be a very uninteresting geometric series if it actually had r equal to 1. It would work, but it just wouldn't be very interesting. So any value that's raised to that power that's bigger than 1 or less than -1, right, is going to make this be divergent. All right, let's take a look at another type of series. This is a telescoping or collapsing sum. Both of these terms are used. Your book focuses on the word telescoping. That's actually what I've learned it as well. But collapsing actually is a little bit more descriptive of what's going to happen here. So this is a type of series where the partial sums are used. Okay, we're going to write out some of the series of what's going on. And things start to cancel each other out. Pieces of this just fall away. Okay? So we're going to do an example of that. And you don't know that this is what's happening until you write some of the sequence out. That's something else. You can't identify like you could on that geometric one. It's not like there's just a pattern to follow. Okay? So you have to write some of them out to actually see that this is going to happen. So this is an example of a telescoping series. So we've got a summation from k equal 1 to infinity of 1 over k times k plus 1. Now, it's going to be most helpful for us to do a little bit of something you did back in Calc 2 to see these collapsing terms actually collapse. What we're going to do first is we're going to use partial fractions. Do you guys remember partial fractions? Okay, we're going to do that first in order to rewrite this as two separate fractions instead of this fraction with this denominator that's got a multiplication factor in it. Okay? So the first thing that you would want to remember from partial fractions is that you have each of the two separate factors of the denominator as a denominator of a fraction. You guys remember that part? The next thing you do with partial fractions is you've got to figure out what the numerators are. So generically right now I'm going to call them A and B. And then what we're going to do, it sort of seems like I'm moving in the wrong direction, we're going to multiply it all back together. Because what I want to do is I want to compare it to the original fraction that I had back before I separated these out. So if I were to multiply these together, I would have A times K plus 1, and I would have B times K over K times K plus 1. And this numerator also then could be written as AK plus A plus BK, which is the more helpful way of seeing it written. Now what I'm going to do is I'm going to compare that to the first numerator pretty much. The denominators match already, but it's the numerator that I'm interested in. All right, so I need the values for A and B to be something that when I put the pieces all together right here, I end up with the number 1. So if you take a look, the number 1, the numerator that I was originally starting with, it doesn't have a K in it, right? So I have terms that have K in them, and then I have terms that are numbers. And I know everything looks like a letter, okay? So you have to be a little bit careful because we're also not using X, which is the normal value that you're using when you're doing calculus, too. But the K's right here are equivalent to what our X's are. So these K terms, I'm going to sort of collect them, and I've got an A plus a B. And I know that that has to equal 0 because there are no K's in the first original fractions numerator. Now the numbers, the only terms in this numerator right here, AK plus A plus BK, that are numbers, they're just constants, is this A in the middle. Is everybody good so far? AK and BK at the end are both multiplied by K. So they are not, they're linear factors, that's what they are. They're like being multiplied by X, if you were dealing with a function in terms of X. The term A in the middle is not multiplied by X. It's a standalone number. It's some kind of a numerical value. That A value right there has to equal the numerical value that I was originally given, which was the number 1. Because I know now that A is 1, I can also figure out what B is. What's B? B is negative 1. Because they have to add up to the number 0. I'm not reteaching the partial fractions, but that's where this is coming from. Okay, so if you're a little rusty on partial fractions, that's where you want to go back to look at this piece of information. What that does is it allows me to rewrite this partial sum, or sorry, this series rather, K equals 1 to infinity, as A is 1, so 1 over K, whoops, and then I've got plus, and then it's B. Well, B is negative 1, so I could actually write this as minus, and then it's 1 over K plus 1. Okay, everybody good so far? Okay, what I'm about to do is not prove that this works as you go to infinity, but I'm going to show you what's happening by writing out a series of terms, okay, a list of these terms. So I'm going to erase just a little bit from my screen to give myself a little more space. And we're going to write out some terms. So we're going to start out with what in the world happens when K equals 1. When K equals 1, I have 1 over 1 minus what? 1/2. What happens when K equals 2? What happens when K equals 3? That's a terrible looking 3. This is going to continue. There's my dot, dot, dot here at the end. But take a look at what's going on here. Do you see anything disappear? Simplify, cancel out, or collapse? Yeah, this negative 1/2 and this positive 1/2, well, those cancel out. And this negative 1/3 and this positive 1/3, those cancel out. And it's going to keep going, right? So the only thing I'm going to be left with is the first term, which was 1, and the last term, which arguably is 1 over K, or n, or whatever you'd like. We'll use n just because we already used k. 1 over n. It's whatever the last term is. And this happens, or n plus 1, technically. And as the n value goes to infinity, what happens to 1 over n plus 1? This value approaches not 1, 0. This value approaches 0. As n goes to infinity, 1 over n plus 1 gets infinitely large on bottom. So you're dividing 1 by something that's infinitely large. And so it approaches 0. So as n goes to infinity, the sum of this telescoping series or this collapsing series is actually the value 1. Now, it doesn't always simplify quite so cleanly when you're doing a collapsing sum. It doesn't have to be that the second piece right here, like with these two, say the 1/2's matched up right away, and the 1/3's matched up right away. You might actually have to write out 3 sets of parentheses before you see the cancellation, or something like that. Yes?
You have 1 over n plus 1 equals 3, it's supposed to be 0, right?
I'm sorry. You mean this piece?
No, right next to it.
This piece?
No, that.
Oh, yes, you're right. I do have that written wrong. Thank you. Let me fix that. I don't even mean equals. I mean approaches. Thanks, Nathan. Yes. So we end up with the value 1. So you can't always see the collapsing part of it until you write out more terms than what are here. Here we can see it pretty quickly because they just happened right in a row. You might have to see more of the terms written out before you see the collapse part of it. Any questions on that one? All right, let's take a look at Theorem 2. Oh, I had myself more space and I didn't use it. Theorem 2.2. All right. If we have a series that converges, okay, so far we've been deciding whether or not a series does converge. But if we have a series that converges, then it is true that the limit of the sequence goes to 0. Okay? Now think about why that has to make sense. Let's say that the limit of the sequence went to 3. We've had that happen on some of the problems you guys were working with where the limit of the sequence was something other than 0. But what a series does is a series continually adds values to something you already have, right? So if the limit of the series is 3, and then you continually add the number 3, or something very close to 3, to a summation you already have, what's going to happen? This is audience participation time. What's going to happen? If you start out with 100 and I add 3 to it, and then tomorrow I add 3 to it, and the next day I add 3 to it, and I keep adding 3 to it, what's going to happen? It gets infinitely large, right? Is it ever going to stop getting bigger? No. So the only way it's going to stop getting bigger is if the value I add is smaller every time. Make sense? That's all this is saying, is that if I'm going to have something that's going to converge, then it must be that the value that I add each time gets very, very close to nothing. Okay? So the image in your mind might actually be a wrong image, and we'll talk about why in a minute, but the image in your mind might look something like the graph of 1 over x. Right, where the graph sweeps down and it gets really, really close to the x-axis and gets infinitely, infinitely small. Okay, that's a correct image, but the graph of 1 over x actually doesn't work, and I'll tell you why in a minute. This also produces a very nice way to show something diverges. So now we're sort of doing things in reverse. We're saying this actually is going to be able to allow us to look at something and say, I know this diverges. Instead of asking myself, does it converge, or testing or doing something to actually test that it converges, we're going to actually be able to look at something and say it does diverge. In particular, we're going to say, hey, look, if the limit of the sequence is 3, it's not going to converge because the limit has to be 0 for that to work. Okay? So let's take a look at that divergence test because that's actually the next thing written down here. If the limit of the sequence does not equal 0, then the series would diverge. That's what I was arguing. If you had something where the limit was 3, so you're consistently adding a number that's getting very, very, very close to 3, All right, so today I add 250, and tomorrow I add 260, and tomorrow, the next day I add 270, and then I add 280, and then I add 288, and then I add 292, and then I add 297. I'm getting closer and closer to the number 3. I'm still adding something that's getting bigger every time. And there's no way for it to stop getting bigger if the limit's 3. So, I may have mentioned this back on the bottom. I'll talk about this in a couple of our other classes. These two, this theorem and this test for divergence, are what are called contrapositives. Right? So one of these can be written, and I want to show you this to you, as a statement that is if P then Q. So if P happens, then Q automatically happens. The other one is actually taking the opposite of Q, or the negation. We're taking the opposite of the result and saying if the negation of that result happens, then it automatically has to be true that the original hypothesis is false as well. These are contrapositives, or logically equivalent statements. They really are the same statement. So we're going to take this fact and we're going to take a look at an example. On this example, we're asked to find if a series converges or diverges. If it converges, find the sum of the series. Well, one of the things that's good to look at is to see, do we even stand a chance? Because if the limit of the sequence doesn't go to 0, then we don't stand a chance. So that's what we're going to look at. We're going to look at the limit of the sequence. So the sequence is this portion of it right here, without the summation at the beginning. And we're going to find out what in the world is the limit of 3k over k plus 4 as k goes to infinity. Now, you've done some of these already, because that's what happened in 9.1. So what could you do here to see what this sequence's limit is? What did you guys do in class last time on the boards?
Multiply by 1 over k.
Right. Multiply by 1 over k on the top and bottom. If I do that, I have the limit as k goes to infinity of 3 over 1 plus 4 over k. Now what? Do you want to finish it for me, Micah? Tell me what's going on.
I mean, you plug in infinity more or less, which would leave with 3 over 1.
Yep. So the 4 over k goes to 0 as k goes to infinity. And just like Micah said, that leaves me with 3 over 1, or the value 3. Maybe that's why I kept harkening on the value 3 just a minute ago. I'm not sure. So my limit's 3, which means it diverges. Because, okay, let's be really careful. The limit of the sequence exists, and it's 3. Agreed? So the limit of the sequence is 3. The problem, however, is that what I'm asked to find is whether or not the series converges. So this series diverges because the limit of the series won't exist because I keep adding things closer and closer to the number 3 every time. The sequence converges, but it converges to something that's not 0. And that's what the kicker is for making sure that it won't end up working, basically. Okay. One more theorem before I get to show you that the opposite of this theorem doesn't work. All right, theorem 2.3 says the following. If we have a series that converges to A, we have another series that converges to B, and we talk about adding or subtracting the individual terms of the series, A sub k plus or minus B sub k, then they converge to that capital A plus or minus that capital B, the limit of each of the individual sequences. And it works for scalar multiplication as well. So if we had C times the A sub k, it would just be C times the limit of what's going on with k. Or the summation of what's going on with the A sub k's. And then likewise, if we had a series that converges and one that diverges, okay, so one's converging, the other's diverging, and we try to add them together or we try to subtract them, and one converges and one diverges, then the whole thing is going to diverge. It's like adding something that goes to 3 together and something that goes to infinity. Well, it's still going to infinity, right? You guys may have had these arguments with somebody before or something where they'd be like, well, we'll say it in a nice way. We'll say that my son says, I love you. I say, I love you twice as much. And he says, I love you to infinity. And I say, I love you to infinity plus 1, right? Well, it's still infinity. That doesn't really work. Same kind of idea. So this part right here down here, number 2, that's what's going on here. We're adding something to infinity. It's still just going to diverge. It's still infinity. Okay. This is actually really nice, and this happens with limits too. You saw this kind of a definition when you did limits back in Calc 1. It also works for integration with pluses and minuses and scalar multiplication. So you saw these kind of a rule or property theorem when you did integration. So we're going to use this property, and we're going to use it for this. So this particular sequence, series, which has two pieces of it that are making up the sequence in the middle, can be done separately. So the first thing I'm actually going to do is I'm going to rewrite this and consider each piece separately. So this is 1 over 2 to the k, and then I've got the subtraction of the summation from k equals 0 to infinity of 1 over 3 to the k. So we're able to do that by theorem 2.3 above. I mean, that's why we're able to do that. That's what theorem 2.3 says I'm allowed to do. Okay? Those are actually sequences we've already dealt with today. They don't look quite the same because they aren't written quite the same, but they could be written the same way. What kind of sequences are 1 over 2 to the k and 1 over 3 to the k? They're geometric. You guys see it? Now, if you're not quite seeing it, you can actually draw it in a way that you can see it a little bit better. This is 1 over 2 to the k. This is 1 over 3 to the k, because of course if you apply k to the numerator of 1, it doesn't change it. So this is what we've got here. So we're going to find each individual, whether or not these each individually converge or diverge, and then we're going to go from there. So the first question you have to ask yourself is, do these converge? Here, I see like 3 nods. They do converge. Why does the first piece of 1 over 2 raised to the k converge? The r value is less than 1. And the 1 over 3 converges for the same reason, right? So we're going to write ourselves down a note that these both converge because 1 over 2 is less than 1 and 1 over 3 is less than 1. It's a geometric series. They're geometric series, and the common ratio or the ratio is actually less than 1. So then what we're going to do is we're going to actually find the summation of each of those. So the first one that had the 1 over 2 to the k, what's the a value on this one? It is 1, right? It doesn't really look like there's anything there, so we understood there's an understood 1 at the front. So this is 1 over, and the formula that we're working with here is a over 1 minus r. The r value is 1/2. So this is 1 over what? 1/2, which gives me the value of 2. So the first piece of this series converges to 2. Let's do the same thing for the second piece. This is a summation from k equals 0 to infinity of 1/3 to the k. So this is 1 over 1 minus 1/3, which gives me what? 1 over 2/3, which is 3/2. All right, now going back to the original problem. The original problem said I was supposed to do k equals 0 to infinity. Not the original problem, but after I separated them. It looked like this. Agreed? So what am I going to do now? Right. Subtract the 3/2 from the number 2, which is going to give me a grand total of 1/2. So we've broken down something that was a summation into individual pieces, and we applied the geometric series to those individual pieces. All right. I want to show you something that I alluded to before. I told you the image of the rational function 1 over x was the right image to have in mind when we're talking about something, a series rather, converging or diverging. But I also mentioned to you something about the fact that that's not quite right. Yeah? All right, so the series 1 over k, as k goes from 1 to infinity, is called the Harmonic Series. Okay, and we're going to investigate what happens with the Harmonic Series. The first thing that we're going to do is we are going to notice that the limit of the sequence here at least means it stands a chance at converging. If I were to take the limit as k goes to infinity of 1 over k, what would this be? It's 0. All right. Now, go back on your notes to the previous page real quick, and I want you to take a look. The fact that this, or sorry, 2 previous pages. The fact that this is 0 does not tell us that the sequence, or that the series converges or diverges. Theorem 2.2 starts out telling us if something about the series happens, then I know something about the limit happens. So that doesn't apply, because I'm talking about limits right now. I'm talking about the limit, right? The second part of this, where it talks about the kth term for divergence, says if the limit is not 0. Well, my limit is 0, so this one doesn't apply either. Okay, so neither of these theorems, or these derivations of the same theorem really, fit with what's going on here. Agreed? Okay, but what we do know from that divergence theorem is that it might converge. At least that divergence theorem didn't tell us we know for sure it diverges, right? So this may converge. At least we don't know for certain it diverges. Yet. So the next thing we're going to consider is some partial sums. We're going to consider the sum S sub n from k equal 1 to n of 1 over k. So this will be the term 1 over 1 plus 1 over 2 plus 1 over 3 all the way out to 1 over n. Because this says I'm going to start at k equal 1 and go up to k equal n. This is the nth partial sum. S sub n corresponds, I'm about to draw a picture, so leave yourself a little space for a graph, corresponds to the sum of the areas of rectangles. I'll go back to the slide just a second. Let me write the word rectangles down. Okay, so I'm going to draw you a picture that shows what I mean by that. So what we're going to draw is I'm going to draw the picture, or the graph, actually, of 1 over x. So this graph looks something like this. Agreed? If I'm talking out about the value at x equal 1 or n equal to 1 in our case, we're here at 1, here's 2, here's 3, here's 4. And my value here at 1, although the image is sort of zoomed in, would have to be the value of 1 here. Here's 2, we're at 1/2. Then we're at 1/3 and we're at 1/4, okay? Because this is y equal 1 over x. Now, if I were to make rectangles of those heights, no promising that I've got these straight. The area of each one of those rectangles will be the width of the rectangle, which is what? 1 times the height of the rectangle. And the height of each one of those rectangles are 1, 1/2, 1/3, 1/4. Okay? So these rectangles all have area 1 over 1, 1 over 2, 1 over 3, and so forth as we continue to go. So this summation of adding 1 over 1 plus 1 over 2 plus 1 over 3 has a graphical interpretation that would match up with this picture. So far, so good? So S sub n corresponds to the sum of the rectangles in and each rectangle lies above the curve y equal 1 over x. Right? All those rectangles are above my curve. You guys remember doing things with Riemann sums and estimating rectangle areas. So what this is telling us, so S sub n is this sum of rectangles, which is greater than or equal to the area under the curve. Agreed? It's more than that area that's actually under the curve. Once I used area under the curve, that phrase, that should conjure up in your memory something from Calc 2. Integrals. So this area under the curve would actually be the equivalent of an integral from 1 to n plus 1, because that's where the rectangles are each ending, right? My third rectangle ends at the value 4. So that's why this is ending at n plus 1. Of 1 over x dx. And do you remember what the antiderivative of 1 over x is?
Natural log.
Natural log, very good. And it's actually the absolute value of the x, but our values that we're plugging in are already positive here, so we can really call it natural log of x. So this will be the natural log of x, and we'd be evaluating at n plus 1 and 1. So this would be the natural log of, again, n plus 1 minus the natural log of 1. Natural log of 1 is actually 0, so that doesn't affect anything. So this is actually the natural log of n plus 1. This would be what we would get. What happens as n goes to infinity inside of that natural log? What happens to natural log values? What happens to the graph of a natural log as n goes to infinity, or as x goes to infinity? It does. It gets infinitely large. If you were to graph it, you'd get an image that looks something like this. This is very rough, right? But that's a sketch. It levels. I mean, it looks like it's leveling off. It's not very steep, right? But it definitely still keeps going uphill. Okay, it's concave down, in other words, but it's going uphill. Okay, it's increasing forever. So this right here, this graph, or this value of this natural log, this is infinity as n goes to infinity. So S sub n is actually greater than or equal to infinity, which sounds funny. It's not really. But it's larger than the sum that we know is infinity already. Okay. Hence, the sum from k equal 1 to infinity of 1 over k diverges. And I'm going to write this in parentheses because I want to emphasize the fact, even though the limit as k goes to infinity of 1 over k is 0. Even though the limit is 0, we still end up with something that diverges. Okay? When we get into 9.3, we'll figure out how it is we make the decision on when that 0 actually matters and when that 0 sort of doesn't help us out, kind of like this one. But in general, what this is telling us about the harmonic series is that the converse of theorem 2.2 isn't true. That is, that if we have the limit going to 0, we don't know for sure that the series converges. Okay, that's what that example actually shows us. All right, we're going to do one more example. On this example, we're going to actually take the information and go in a little bit different order. On this one, we've got a C value, if you will. There's a C inside of our sequence formula. And our summation goes from k equals 0 to infinity of 2 over c minus 3 to the k. And the directions say to determine the values of c so that this thing will converge. Okay? So what kind of a sequence or series, whatever, what do we have here?
Geometric.
It's geometric, right? So we know that a geometric series will converge when what happens? Right. And so let's actually identify what in the world our A value and our R value are here. So what is A in this problem?
2.
It's actually 2. What is R?
1 over C minus 3.
Right, 1 over C minus 3. Okay. So we want that 1 over C minus 3 to the K to actually have the property, not C minus K, C minus 3 raised to the K, to have the property that when we take its absolute value, it's less than 1. So we need to figure out what values for C will actually make this work. And I'm going to show it to you. I mean, some of you probably can look at that and just figure it out in your head, but I want to show you the algebra for doing it because sometimes you aren't going to be able to just do it in your head depending on the problem that you're working with. So the first thing I want you to recognize is that I can take these absolute values independently. So I can actually put the absolute value specifically if I would like. I did not mean for that K to be there or here. Sorry. Just C minus 3. The K value is not part of the R. I can put the absolute values around that C minus 3 independently because the absolute value of 1 is already there. I could multiply the C minus 3 to the other side. So what I really need is I need the absolute value of C minus 3 to be greater than 1, or 1 to be less than that. Okay, so you may remember from algebra that when I have and I'll write it the other direction because I feel more comfortable with it written this way. I've got the absolute value of C minus 3 greater than 1. This becomes 2 separate inequalities. One inequality says that C minus 3 is greater than 1. The other inequality says that C minus 3 is less than negative 1. That's college algebra concept. You may not have seen that in a while, but that's where you not first encountered it, maybe last encountered that. And then we'll end up finding out that C has to be greater than 4, or C has to be less than 2. So if I have a C value greater than 4, or C value less than 2, I will end up with a value in the denominator that is bigger than 1, so that my fraction will be less than 1. Okay? Any questions on this? This one's algebra is probably years ago for you guys at this point, because you've had a lot of math since then. Okay.